Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering Module 11 IPv4 addressing. This presentation is about an hour long, and it's really an overview. I've created 3 more videos, each an hour long, to really go further in depth in subnetting, so please watch for those videos. Watch this one as an overview. If you understand this and you get subnetting, then you don't need to watch the other 3 hours of videos. Although I absolutely recommend watching the VLSM subnetting video if you have any questions about VLSM. Okay. I'm going to go ahead and share my screen. And I need to move this 1 second. Start the presentation. And I have to minimize this. If you're watching this live with me, there will be a period to ask questions and answers at the end of the presentation, so please wait. If you're watching this inside of NetAcad as a recording, then please ask your questions in our help discussion forums. And if you're watching this on YouTube, please ask your questions in the comments below my presentation, and I will do my best to answer those questions, although feel free to answer each other's questions. That is awesome when you do. All right, so today's objective is to calculate an IPv4 subnet scheme to sufficiently efficiently segment your network. Now we're going to describe the structure of an IPv4 address using the network portion, the host portion, and the subnet mask. We'll compare the characteristics and uses of the unicast, broadcast, and multicast IPv4 addresses. We'll explain public, private, and reserved IPv4 addresses. We'll explain how subnetting segments a network into to better enable communication. And we'll calculate IPv4 subnets for a /24 prefix. And then briefly at the end, we'll challenge all our brains. We're talking about a 22 subnetting into the third octet. But don't worry about that yet. We've got a lot to learn before we get to that point. We'll start off with IPv4 addressing to grow a little bit more knowledge from where we were a couple modules ago. An IPv4 address is a 32-bit hierarchical address that is made up of a network portion and a host portion. When determining the network portion, this is the network portion and that's the host portion. When determining the network portion, you must look at the 32-bit stream of ones and zeros. The subnet mask is used to determine the network portion and the host portion. Hang on a second. Let's go to the next slide. So again, this is the network portion, and this is the host portion of the network, the IP address, and the subnet is how we determine what is the network portion, what is the host portion. We'll see that slide again. Now, a subnet mask address can also be referred to as a prefix length, and it is less cumbersome method to use to identify the subnet. A prefix length is a number of bits set to 1 in the subnet. You just count them. It is written in slash notation. Therefore, just count the number of bits in the subnet mask and prepend it with a slash. So here, for example, we have 8.1, so you have a /8. This is 16. This is an A network. This is a Class A network, Class B network. We have 16. This is a Class C network. We'll spend a lot of time working with Class C networks. And then we subnet. Generally, we subnet from a /24C network. And we subnet into 25. Look, we just have one more address, one more one. Therefore, we go from 24 to 25, 26, all the way down to 30. 30 is the smallest slash notation that we can use in a LAN. We can go to a 32, but that's one address. 31 doesn't really have a purpose in LANs, at least. Now, the subnet mask is used to identify the network and host portions of the IPv4 address. The subnet mask is compared to the IPv4 address bit for bit from left to right. The actual process used to identify network and host portion is called ANDing. Now, the way ANDing works is you compare the subnet and the host address, the IP address, the IP of the host, and the subnet. And if it's a 1 and a 1, you get a 1. If it's a 1 and a 0, you get a 0. 0 and a 1, it's a 0. 0 and a 0, obviously a 0. It's the Boolean AND that we're doing, and the only thing that results is a 1. Now, once we do the ANDing process between the host address and the subnet mask, that gives us our IPv4 network address. Remember, we'll be working with networks. I often say the 10 network or the 20 network, and inside the 10 network, there's 256 addresses, for example. But how can you find out what if you have an IPv4 address like 192.168.10.5, how do you know what network that's in? Well, the way you know what network's in is you do this ANDing process with the subnet mask, and it tells you the network address. I actually have a video to show you how that works right now. So let me pause my video, and I'll get that video ready to go, and then I'll bring you all. Okay, I've got that video ready for you. Here we go. This is video 11.1.5, network, host, and broadcast addresses.
All devices on an IPv4 network need a 32-bit logical address in order to communicate. This 32-bit logical IPv4 host address consists of a network portion or network ID on the left and a host portion or host ID on the right. The length of these depends on the size of the network. Larger networks will have a longer host portion. A network can be thought of as a range of addresses. All devices on the same network have the same bit pattern for their network ID, but they will have a different host ID. Some addresses in this range are reserved and have a special name and meaning. For example, the first address in the range is used to identify the network itself and cannot be assigned to any host. It is referred to as the network address. The last in the range is called the broadcast address and is used to send a message to all devices on the network at once. It also cannot be assigned to any host. All the IP addresses between the network and the broadcast addresses make up the usable or valid host range and can be used to address the hosts on the network. Let's take a look at how these addresses are determined. In order to forward data, a device needs to know what network it's on. Using their host IP address, their subnet mask, and a process called binary ANDing, a device can find what's referred to as the network address. This address represents the network to which the host belongs and will be slightly different than its host IP. To do this, the device compares their host IP and their subnet mask bit for bit. If the bit values are both a binary 1, the result is a binary 1. If one or both of the bit values is 0, the result is a binary 0. Let's take a look at an example. Let's say we have a PC with a host IP address and a subnet mask of 192.168.2.38/24, and we'll use ANDing to find the network address of the host. Here's the host IP in binary. Here's the subnet mask in binary. If we compare them bit for bit, we can see that a 1 and a 1 results in a 1, a 1 and a 1 results in a 1, a 0 and a 1 results in a 0, a 0 and a 1 results in a 0, and so on until we have compared all 32 bits. Notice that the last octet is all binary zeros. Because we are using a /24 subnet mask, the first 3 octets represent the network portion, and the last octet is the host portion. Network addresses will always have binary zeros in their entire host portion, however long it is. In this case, the last 8 bits. If we convert to dotted decimal, we can see that this host belongs to the network 192.168.2.0/24. Now let's determine the broadcast address for this network, which is used to send a message to all devices on the network at once. Whereas the network address had all binary zeros in the host portion, the broadcast address will have all binary 1s. Since the host portion in this example is just the last octet, To determine the broadcast address, we keep the network portion the same and change the host portion to all binary ones. This results in a broadcast address of 192.168.2.255. Next, we'll determine the usable host addresses, which lie between the network and the broadcast addresses. The first usable host in binary will be all binary zeros with a binary 1 at the end of the host portion. Converting to dotted decimal, this tells us the first usable host on this network is 192.168.2.1. Lastly, we'll determine the last usable host, which will be all binary ones with a 0 at the end, the opposite bit pattern of the first usable host. Converting to dotted decimal, we get 192.168.2.254. Let's recap our calculations. We began with the host IP address of 192.168.2.38/24. Using binary ANDing, we determined that this host belongs to the network 192.168.2.0. Keeping the network portion the same, but placing all binary ones in the host portion, we determined that the broadcast address for this network is 192.168.2.255. Again, keeping the network portion the same, but changing the host portion, we determined that the usable host range for assigning addresses to devices on this network is 192.168.2.1, which is one number up from the network address, and 192.168.2.254, which is one number down from the broadcast address. You can see that our original host IP address falls within this range. Things to keep in mind when working with IPv4 addresses. All IPv4 host addresses are 32 bits in length. A portion of the address represents the network that the host belongs to, and that starts at the left. The remaining part is the host portion, which identifies the host on the network. And there are two special reserved addresses on every network that can't be assigned to hosts. One is the network address, which is the lowest in the range of addresses and represents the network that all the devices belong to. And the other is the broadcast address, which is the highest address in the range and can be used for a shout out to all devices on the network at once. Thankfully, there are shortcuts you can take for calculating these addresses without having to convert to binary first. But examining these addresses at the bit level should help you understand how network devices interpret them and also how the dotted decimal format is derived.
That's a good starting point. Let's keep going with the presentation. All right. We are going to see this slide, which again reiterates what she was just saying. So within each network are three types of addresses: the network address, the host addresses, and the broadcast address. And when you're looking at them, you can see here the network, the 10 network, is in each of these addresses. A /24 means you have 256 addresses, and 0 is the network address in a 24 network. And then they've assigned the first address to the router, and then they've assigned various addresses to the other hosts. And you can see that on this list in the table. IPv4, unicast, multicast, and broadcast. So a unicast transmission is sending a packet from one source to one destination, a source to one destination. For example, the PC at 172.16.4.1 sends a unicast packet to the printer at 172.16.4.253. This is .253. It's not going to, the other devices do not see it. Now, on the other hand, a broadcast comes from one device and it goes to all nodes on the switch except for the one that it was the ingress address. That's broadcast. For a /24 network, that's all 25. That's all that's 255. That's the address 255. That's a 24. If it's a 23, it would be it could be 127 or 255, and you'll learn that when we talk about subnetting. And then multicast is coming from one address and going to multiple, but not all addresses. That's a multicast group. Now, what are the types of IPv4 addresses? Well, as defined in RFC 1918, public IPv4 addresses are globally routed between internet service providers. Now, we used to hand out IPv4 addresses, but then as we learned earlier, with only 4.3 billion addresses, we started running out of those addresses. So they came up with private addressing. Private addressing are common blocks of addresses used by most organizations assigning IPv4 addresses to internal hosts. Now, private addresses are not unique. So in my home, I might have a 192.168.0.1 router port, and you might also. So that's why routers never pass these private IPv4 addresses. And the addresses are in the range 10.0.0.0.8, and these are the exact addresses, 172.16.0.0, and then 192.168.0 here, and this is where we do a lot of learning in this class in that range. Now, network address translation is that translation between private IPv4 addresses, the ones I just showed you here, these private addresses, and public IPv4 addresses that are not in those other ranges. NAT is typically enabled on an edge router connected to the internet with one routable address, and then that router turns that one routable address into multiple hundreds or thousands of addresses for private networks. And here you can see they show all of the 10 network, the 16 network, and the 192 network. And they show each of these networks all talking to an edge router, and then the edge router has a private address that talks to the IP, the ISP. Now, there's a couple more special addressing, which includes the loopback address and local addresses, linked local addresses. The loopback address is pretty much anything. It is anything in the 127 network. Normally we see 127.0.0.1 as the loopback address. And what a loopback address does is it allows a computer to ping its own IPv stack. If it works in its own IPv stack, then it's able to communicate. It should be able to communicate outside of itself, and so you can start looking at other issues that are outside of the network. Now, it's used by hosts to test that TCP/IP operation. That's what I just said. Link local addresses. If you're working on a Windows computer and you have a link local address, you actually have a problem, because that means that you are not able to get even a public address. I'm sorry, a private address from a router. So the computer assigned itself a PIPA address, and that's an automatic private IP address. That's what IPIPA stands for, and it's self-assigned. It's useless. It might be able to communicate with other devices in its own network, but when do we ever do that? Really, it is not what. If you see something that starts with 169.254, and you have a problem, and you need to figure out why you're not getting an IP address from your router. 169, that's a problem. If you got 169.254, you've got a problem. Now, back in the day, when they were handing out addresses, they handed out addresses based on classes. So if you qualified or needed thousands of addresses, you got a class A. If you needed or tens of thousands, you got a class A. If you needed thousands, you could get a class B, or class C would be if you needed hundreds of addresses, because when we're talking about the overall scope of addresses, if you have a class A address, you can only have 128 addresses with 16 million addresses that were inside, that were in that range of 192 dot whatever, right? So so there's so you would lose millions of addresses. How many organizations need 116 million addresses, right? Class B has 16,000 networks with 64,000 addresses, 65,000 addresses in each one. Even that is very few organizations need 65,000 addresses in any one subnet. So we do Class C, you get 2 million networks. We don't need that many networks, but 254 addresses is a good number of addresses to be able to break down into smaller networks. Like each classroom at a school could have, there's 24 computers, so you could put each classroom in its own subnet. You got plenty of subnets with 2 million subnets, and so that's where that comes from. Wastes a lot of addresses. And you may still hear people talking about A, B, and C classes, but they're not talking about using classful addressing. They're just saying a class A address is in that /8 realm, and with thousands of private addresses, thousands of addresses, and a class 16 is tens of thousands of addresses, and class 16 is thousands of addresses. But they're not really talking about just using one big class B network. You end up using subnetting to break one group of addresses down into a smaller sets of addresses that you can then assign. Now, the addresses are assigned, the Internet Assigned Numbers Authority, IANA, manages the allocation of blocks of IPv4 and IPv6 addresses to 5 regional RIRs, and they are responsible for allocating IP addresses to ISP, who provide the ISP addresses in smaller blocks to smaller ISPs, and then finally an organization gets their address. And we're running out of IPv6 globally addressable, IPv4 globally accessible addresses. So with subnetting, which is what we're going to talk about moving forward, we're able to expand the number of addresses that are being used by using those private networks. Now, broadcast domains. Many protocols use broadcast or multicast. Use broadcast or multicast. For example, ARP uses broadcast to local other devices. Hosts send DHCP discover broadcast to local DHCP servers. Now, switches propagate broadcast out all interfaces except for the interface in which it was received. Remember, in a /24, for example, that would be a 255, and that would be the broadcast average address for a /24, and all devices on that network would get the result. But the only thing that stops a broadcast is a router. Routers do not propagate broadcast past its border. So a router, remember, it divides networks. So a router, this is one network, and on the other side it has another network, and their broadcast will never pass. Each router interface connects to a different broadcast domain, and broadcasts are only propagated within the specific broadcast domain. A problem with large broadcast domains are that these hosts can generate excessive broadcasts and negatively affect the network. The solution is to reduce the size of the network to create smaller broadcast domains in a process called subnetting. Dividing the network address 172.16.0.0.16 into 2 subnets of 200 users each. Now we have smaller broadcasts. You have a broadcast on this side in the 0 network, and you have 200 users in this side, in the 1 network. So of course, there's many more addresses than 200, but that's what they're showing as what we need, and so that works. Now, subnetting reduces overall network traffic and improves network performance. It can be used to implement security policies between subnets. For example, the student subnet can't bleed over into the faculty subnet because you guys might want to change some grades, for example. And the faculty can't bleed over into HR because if we can figure it out, we'd be giving ourselves raises all the time, at least until we're caught. Subnetting reduces the number of devices affected by abnormal broadcast traffic. So if you were to have a broadcast storm, for example, it would only affect those devices that are being in that subnet, not into the entire building. In this example, they have a building that has been divided into 5 floors, and they only show, let's see, that 5 floors, where they show here. Yep, sure enough, they have 5 floors and 5 subnets, but then they only show you, oh, they're saying you could break your subnets based on floor if you want to base it on location, being the first LAN or the first network is the first floor, second, third, and way up. Or you can group it by function. That's the way they do it at our school. Administration has its own network, and the way HR probably does, students definitely do, and then faculty is on the admin LAN. And then device, actually, we're on the FSCJ network at the school I teach at. And then device type, here it could be maybe you have one network for all hosts, one network you have for all services, servers, another way maybe for all printers, etc. Subnetting an IPv4 address. Networks are most easily subnetted at the octal boundaries of 8, 16, and 24. We'll see that later when we subnet a 22 network. It's challenging, a little bit more challenging than it is, again, an 8, a 16, or a 24 network. So notice using longer prefix lengths decreases the number of hosts per subnet. So if you have a /8, you have 16 million hosts, but you have fewer networks. There's a chart on the next page, I believe. In a 16, you have 65,000. I guess I could have said earlier when it's the /8, the millions of addresses. I said tens of thousands. Actually, the 8 has millions. The 16 has tens of thousands, and the /24 has a couple hundred addresses, but lots of subnets. And here, for example, with subnetting on the octal boundary for a /8, and you can see that the first network is 10.0.0.0, 10.0.0.0/16. The first address is .1. The last address, look at this, it's 10.0.255.254 because the broadcast is 255.255. And that's the 0 network here. And then we have the 1 network, the 2 network, the 3 network, and then they do ... And that gets you to the very last subnet, which is the 10. This is the 10.255.0.0.7 all the way up to 255, right? And that gives you the first address in this range is .0 is .1. The last one is 255.254. And the subnet is 10.255.255.255. All right, so that is the 10. This is this should be the /8. Here is a /16, and you can, no, actually the 24 is here. They did a 16. We're missing the 8. Where's the 8 on this chart? They only show you the /8 is subnetted. I see. We're breaking the /8 into a /16, and then here we're breaking it into a /24. Now refer to the table to see 6 ways to subnet a /24. So a /24 network can be broken in half. That gives you 2 subnets of 126 addresses. Those 2 could be each broken up in a half, and they could be broken, and they can be broken. We get all the way down to 64 subnets of 2 hosts. And as we increase the number of subnets, we decrease the number of hosts. And what we're really talking about is borrowing bits. We're gonna watch this video, the Subnet Mask, to give you guys an idea of how the Subnet Mask works. Let me bring it over and start it.
Now, I want to take a moment to point out that subnetting makes sense from perspective. In other words, we take the IP address and the sub.
All right, my computer presentation stopped there for a minute, so I'm going to go back to the beginning again, and I won't pause it again. So here we go.
Now, I want to take a moment to point out that subnetting makes sense from the binary perspective. In other words, when we take the IP address and the subnet mask and convert them to binary, I have the IP address on this row here, I have the subnet mask on this row, converted to binary, that the computer and the router are able to logically AND or combine the IP address and the subnet mask and find the network address. In other words, this ANDing process is a logical process of ANDing. So a true and a true makes a true, 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 false and a true makes a false. And if we do that and logically AND the IP address with the subnet mask, we get the network address. So 192.168.1.10 logically ANDed with 255.255.255.0 produces the 192.168.1.0 network. This is at the core of the IPv4 address and subnet mask and subnetting in general. What about non-classful subnet masks? We've seen that the class C subnet mask is /24. We've seen the class B subnet mask /16 and the class A subnet mask /8. But what if we use classless masks? In other words, what if we have a /25 subnet mask or a /18 subnet mask, creating a 255.255.192.0 subnet mask? Or for that matter, a /12 subnet mask, 255.240.0.0. How does that work? And how does that change the networks that are created by the combination of the IP address and the subnet mask? This is called subnetting. I'll explain it using an example scenario. Let's start with a classic Class C network like 192.168.1.0 with a /24 or 255.255.255.0 subnet mask. If we want to subnet this 192.168.1.0 network, what we need to do is go into the subnet mask in binary, which we can see on this row right here. And what we do is, to change the subnet mask, we borrow bits from the host portion of the address. This is done from left to right. So I could take this first 0 here on the left and change it to a 1. And now I've effectively changed the subnet mask from /24 to /25. In other words, if I convert this back to decimal, it's now 255.255.255.128. This completely changes the nature of the network. We now have a /25 subnet mask, and we only have 7 host bits. So starting from a /24, we now have borrowed 1 bit from the host portion. We call this 1 bit a subnet bit. If we look at it from the perspective that we started with /24, we've added 1 bit. So we could say that subnet bits, we now have 1 bit or 2 to the first power, creating 2 subnetworks. Host bits, we have 7 zeros now. So host bits are 2 to the 7th power or 128, minus 2 for the network address and the broadcast address, leaving us with a total number of possible hosts on the subnets of 126. So by borrowing 1 bit from the host portion of the address, we create 2 subnetworks, each subnetwork with 126 hosts. The subnetworks are the 192.168.1.0/25 subnetwork and the 192.168.1.128 subnetwork /25. We can prove that this is the case using logical ANDing to prove how the router or computer would take an IP address with this particular /25 subnet mask and derive the resulting network address. In other words, let's put in a host address. I'll put in the host address here, and I'll say, let's put in the address 68. So I changed this to a 68. So now we've got host 192.168.1.68. So this needs to be a 1. That's the 64. And then we need to add the 4-bit here. So now we have 68. If we logically AND the IP address here with our new subnet mask /25 here, let's see the result. We'll get a 1, a 1, 0, 0, 0, 0, 0. So that's 192. And then here, the result is 101, 01, 168. And then all zeros here and a 1. This is a 1. And now, if we look at this last octet, a false and a true makes a false. A true and a false makes a false. And then we get all zeros here. So the address, the network address, is the 192.168.1.0 network. So host number 68 is on the 0 network. Well, this makes sense because if the next subnet is 128, if we put in a host address larger than 128, we'll see if it falls in this subnetwork. So let's change it slightly. I'll change the host address to 138. So now I'll change this, put that as 0. So there's a 128 bit. I'll make this a 1. And I'll put a 1 here. So 128 plus 8 plus 2 is 138. If we do the ANDing again, we see that a true and a true makes a true. And then we have falses all the way. Now, the resulting network address is 128. So when we take the IP address with the /25 subnet mask, we see that the network address is 192.168.1.128. So we've created 2 subnetworks from the single 192.168.1.0/24 network. We've created 2 subnetworks. The subnetworks go from 1.0 all the way up to 1.127, with 0 being the network address and 127 being the broadcast address. And the second subnetwork starts at 128. So this is the network address because it's the first address, all the way up to 255. And since this is the last address, this is the broadcast address. In other words, the first address in the subnet is the network address, and the last address in the subnetwork is the broadcast address. This process is called subnetting.
Okay. And we got another video to jump into, the magic number. Now, the magic number is, I don't like to call it the magic number. I like to call it block size. But the magic number is very common, very popular. So if that's how you've learned how to subnet, then don't change your mind on how to do that. I'm looking for the video right now. So let's see. Here it is. The magic number. It's not very magical at all. It's just a very useful number.
This video focuses on subnetting and how to find your subnetworks easily and quickly using the magic number trick. Let's say we're subnetting a 192.168.1.0 network /24. I have the IP address and subnet mask in decimal here, and I have them listed in binary here, the network portion of the subnet mask and the host portion of the subnet mask. To subnet this network, what I can do is I can borrow 1 bit from the host portion of the subnet mask, and now I have 1 subnet bit. This changes the subnet mask from /24 to /25. If I borrow 1 bit from the host portion, I have 1 bit, or 2 to the first power, makes 2 possible subnetworks. The subnetworks I've created are the 192.168.1.0 subnet and the 192.168.1.128 subnet, both /25. The hosts on each network are 126 usable hosts. We have 7 zeros here, and 2 to the 7th power is 128, minus 2 makes 126 usable hosts per subnet. If I decide to borrow 2 subnetwork bits from the host portion of the original 192.168.1.0/24 network, I now have /26. I've borrowed 2 bits, so now I have 2 to the 2nd power of subnet bits, so I have effectively 4 subnetworks. The 4 subnetworks are listed here. For host bits, I have 6 zeros in the host portion of the address, and 2 to the 6th power is 64. Minus 2 for each subnet makes 62 usable hosts per subnet. The subnetworks that are created are the 192.168.1.0 subnet, the 64 subnet, the 128 subnet, and the 192 subnet. Notice how the number of borrowed bits and the number of host bits determines a lot about the subnet. If I borrow 3 subnetwork bits, I now have a /27, so it goes from /24 to /27. I have 3 subnet bits. 2 to the 3rd power is 8. 2 times 2 times 2 is 8. And you can see that I now have 8 subnets, or 8 subnetworks, created from the original 192.168.1.0 network. Each subnet is now /27. Notice that there are now 32 hosts, or 30 usable hosts, per subnetwork. We could go up to /28, and now I have 4 subnetwork bits. Notice that the subnet mask has changed from 255.255.255.0 when it was /24 to now 240. I now have 16 subnetworks, or 2 to the 4th power, and there's 2 to the 4th power of hosts per network. So there's 16, or 14 usable host addresses per subnet. Borrowing 5 bits looks like this, and borrowing 6 bits looks like this. I've now borrowed 6 bits from the original 8-bit host portion of the original /24 network, and I now have 2 to the 6th power of possible subnetworks, meaning I have 64 subnets. The host portion of the address is now only 2 bits, or 2 to the 2nd power, meaning there's only 4 host addresses per subnet. Now, if you have 4 host addresses, you have to leave room for the network address and the broadcast address, so 4 minus 2 leaves only 2 usable hosts per subnet. Typically, on a LAN, we do not go higher than a /30 subnet mask. Otherwise, you'll not have enough room for usable host addresses. In other words, we can't borrow any more bits from the host portion, or we won't have enough addresses for hosts. You might be asking yourself how I was able to discern the different subnetworks from the subnet mask, or subnet bits that were borrowed. There are many different ways to derive the subnetworks from the subnet mask, but my favorite is the magic number technique. The magic number is simply the place value of the last one in the subnet mask. So in this situation, we have a /25 subnet mask. We have 25 ones, and the last one is the one here all the way on the right, highlighted in red. This one, if we look at it according to this octet, is in the 128th place. If we think about the place values of 8 bits, this is the 128th place.
I'm going to freeze the video there just for a moment. And the reason why I'm going to do that is because I like to think of subnet as block size. When you're subnetting, you select blocks that fit the number of subnets you need, the number of hosts you need as sets, if you will, if you think about math. So it's different sets of numbers. Now, I call those blocks. These are the blocks, 128, 64, 32, 16. So if you're dealing with 16 the blocks, then your subnets, your IP addresses break down in every 16. If you get 32, every 32, 64. Now he likes to call them block magic numbers. I like to think of it as blocks. And you build with blocks. If you can kind of get the analogy, it might help you to understand the concept. But again, if you like magic number, then you can go with it. It's just referring to the block of addresses that you are assigning. Maybe you can use both magic number and block size.
So the magic number in this situation is 128. The magic number tells us where to find the networks. It tells us that the networks will go up by 128. So in this case, the first network, which is always 0, so 192.168.1.0/25, and from there, the networks go up by 128, so the next network is 192.168.1.128. Let's see how this works, borrowing 2 bits from the host portion. Now I have borrowed 2 bits from the host portion of the subnet mask. The magic number is now the last binary one, which in this case is in the 64's place. So the magic number is 64. The magic number tells us how to find our networks and lets us know that the networks will be going up in increments of 64. So for instance, the first subnet is always 0, so 192.168.1.0/26. The next subnet is 64. 64 plus 64 is 128, and 128 plus 64 is 192. You can see how the subnets are going up by 64. There's only 4 subnets because we've borrowed 2 subnet bits. Also, we can go no higher than 192 because 64 plus 192 is 256, and that's too large a number. Let's see how it works with 3 bits. With 3 bits, we now have a /25, 26, 27 subnet mask, /27 subnet mask, in decimal 255.255.255.224. The last one in the subnet mask is our magic number. In this case, it's in the 32's place in the binary conversion table. So the magic number is 32. If we look at the networks, we'll see that they go up by 32. The first network being 0, 192.168.1.0/27. Then the 32 subnet /27, 64, 96, 128, 160, 192, and 224. The subnets go up in increments of 32, following the magic number. Now that we see the pattern and how the last borrowed bit affects the location of the subnetworks, let's try it with a /28 subnet mask. Now I have the 192.168.1.0/24 network. I want to subnet it, changing it to /28. /28 means I borrow 4 bits in the subnet mask. So I now have 28 ones counted from left to right. 255.255.255.240 subnet mask. 128 plus 64 plus 32 plus 16 is 240. the last one is in the 16's place. This is the 128th place, the 64's place, the 32's place, the 16's place. So the magic number is 16. We'll see that the networks go up by 16. The first network is always 0, so 192.168.1.0/28. I'll copy this and paste it, and the next network will be the 16 network. Why? Because the magic number is 16, because the last one is in the place value of 16. The next network will be 32. And the following network will be 48. And after 48, 64, and so on and so forth. The networks will go up by 16. In each network, we have the host bits, 4 bits for host, which is also 2 to the 4th power of 16. So the network will go from 0 up to 15, with 0 being the subnetwork address or network address, and 15 being the broadcast address. And the next subnet is the 16 subnetwork. Now let's try creating /29 subnets. We can see that that involves borrowing 5 bits from the host portion of the subnet mask, and that the last one is in the 8th place. So the magic number is 8. The networks will go up in increments of 8. So starting from 0, we'll have the 8 network, and the 16 network, and the 24 network, and so on and so forth, all subnets being /29. For the /30, we see that the last one is in the 4's place, and that the networks will go up by 4. So similarly, the networks will go up in increments of 4. So the first network is the 0 network, then the 4 subnetwork, then the 8 subnetwork. Each subnetwork will have 4 host addresses, in this case 0 to 3. 0 will be the network address, 3 the broadcast address, and the addresses between 1 and 2 will be the usable host addresses. Only 2 usable host addresses in a /30 subnetted network. You might ask yourself, will this technique, the magic number technique of looking at the place value of the last one in the subnet mask, work in other subnetted octets? In other words, if we're starting from a class B /16 network address, or a /8 class A network address, would this technique work? And it does. For instance, if we take a 172.16.0.0 network /16, you can see in this scenario, I've subnetted it to a /23 subnet mask. In other words, I've taken the original 16 network bits and borrowed 1, 2, 3, 4, 5, 6, 7 ones from the host portion of the subnet mask. In this situation, the last borrowed one is in the 2's place. So the magic number in this situation is 2. This means that the subnet will go up by 2 in this octet here. So in other words, our first subnet will be 172.16.0.0/23, and the next network will be 172.16.2.0/23. The only difference is now, instead of 16 host bits like we would have had in a /16 network, we now have 9 host bits. So 2 to the 9th power, meaning we have 512 minus 2 would be 510 host addresses that we can assign. In other words, the network goes from 0.0 all the way up to 172.16 0.1.255. So the first usable host address would be 0.1, and the last usable host address would be 1.254. The next subnet starts at 2.0. After that, the networks continue to go up by 2. In other words, the next subnet will be the 4 subnet, and then the 6 subnet, and the 8 subnet. Notice that the networks are going up by 2, but in the 3rd octet, not in the 4th octet. The only difference not to be confused on is the larger number of host addresses that you'll experience when you subnet in this octet or in the 2nd octet. You can see how the magic number technique can help you quickly locate the networks or subnets.
All right, and that example that he just gave where he was talking about a /23, that 23 is going to, if you think about, we went to the left, that is going to come back into play when we get to our last little challenging assignment, because it's one more to the left, a /22, and hopefully that video helped understand what we're going to talk about. Anyways, you're going to learn about about designing a subnet and configuring devices in a packet tracer 11.5.5. We can also subnet a /16 and a /8, and here they show you the /16 network, and here is the /22 that we would have in our the final project. I'm just pointing it out here because I want you to understand when we get to that little final challenge, this is a /22 network, meaning we've gone to the left 2 spots. We've created 64 networks. Each network has 1,022 addresses in it. So that network, that last network where we need 10 addresses, 10 networks, and a few of them that just have 2 addresses in them. That's a really bad example about how to allocate addresses, because we only need 4 addresses, a /30, but yet we are using a /22, which is 1,022 addresses. We're actually wasting 1,018 addresses on all of those point-to-point networks. I'll bring us back to that when we get to that slide. But this slide is really important for you to understand that slide. I wish I could, let me see if I can figure out how to get to here quickly. What slide is this? This is slide 32. Okay, how appropriate. I can remember slide 32. Let's get going, and we will, maybe we'll see this slide again a little bit later on. Now, you can create 100 subnets with a /16. That's why you may use a /16. A large enterprise might need 100 subnets and has chosen the private address of 172.16.0.0/16 as its internal network address. The figure displays the number of subnets that can be created when borrowing bits from that 3rd octet. Notice how there are now up to 14 host bits that can be borrowed. The one that we're looking for is, I believe, this one with 64 addresses. If we go back here, I'm sorry, 64 networks. This network right here, it should be, subnet should be the same as this one right here. And you might need 1,000 addresses. So if you need, I can't imagine, an ISP might need, a small ISP might need 1,000 subnets for its clients using the network 10.0.0.0/8. And that means there's 8 bits in the network portions and 24 host bits being able to be borrowed towards subnetting. And it shows you how that would break down. Now notice we're in the 2nd octet, and we are borrowing from this set of network addresses, and how many networks we have. And here's a video to show that in-depth video, and it is 11.6.5. Nope, 6.4. That's incorrect. Okay, so here's that video.
In classless subnetting, we've seen how we can borrow bits from the host portion of the subnet mask, and that the last one that's borrowed is the magic number, meaning that the last one, if we look at the place value of the 8-bit grouping, the last one in this case is in the 32's place, so the networks go up by 32. Starting with the 0 network, we have the 32 network, then the 64, 96, 128, so on and so forth, but the networks go up by 32. What about when we're subnetting from a class A or class B network address and subnetting generally in the other octets? Let's take a look at another example. This time we have a 10.0.0.0 network address and a classful class A subnet mask, and we're going to subnet it. So we've taken the 8 bits and borrowed 3 bits, and now we have a /11 subnet mask. The last one in the subnet mask is still in the 32's place. If we look at this 8-bit grouping in this octet right here, the last one is still in the 32's place. So the networks will go up by 32. So the networks are the 10.0, 32, 64, 96, and they're going up by 32, but in the second octet. The only difference is now we have a lot more host addresses. We have 8, 16, 21 zeros for hosts, which means there's over 2 million hosts per subnet. For instance, if we take a look at this 10.192.0.0 subnet, the next subnet is 10.224. So that means that the host addresses go from 0.1 all the way up to 10.223.255.254 as the last usable host, and 255 is the broadcast. The next address is 10.224.0.0, which is the next subnet. All of these subnets are now /11. What about a more difficult scenario? In this scenario, we need to create over 300 equal-sized subnets of 20,000 hosts each, starting from the 10.0.0/8 network. So we need to create a lot more subnets, and we need a lot of hosts. Looking at this situation, we know that we're going to need to borrow bits from the host portion of our subnet mask. The question is, how many bits will we borrow? If we borrow 1 bit, we have 2 subnets. Now we have 4 subnets, 8 subnets, 16, 32, 64, 128, 256, 512. If we borrow 9 bits, we'll have 512 subnets that we create, and that will be sufficient to meet the demand for 300 equal-sized subnets. What about the requirement of 20,000 hosts each? We have 15 zeros left for hosts per subnet. 2 to the 15th power is 32,768 minus 2 would be 32,766 hosts per subnet. That meets the requirement of having at least 20,000 hosts in each subnet. So this scenario would work. You can see here that I've now highlighted the borrowed bits from the subnet mask. I've also converted it to decimal here, 255.255.128.0. And I've already ascertained that the last one in the subnet mask is in the 128's place, so the magic number is 128. The subnets will still go up by 128, but they'll also need to go up for every number possible in the second octet. If we look below here, we can see our subnets. the first subnet will be the 10.0.0.0/17 subnet, then the 0.128 subnet, then the 1.0 subnet, then the 1.128 subnet. And as you can see, we're iterating through every possible number in the second octet and then going up by 128 in the third octet. If I was to list out every possible subnet, we'd go all the way up to 10.255.0.0, and the next subnet would be 10.255.128.0/17 is our last subnet, for a total of 512 subnets. In a situation like this, there's many more subnets and many more hosts per subnet, but the rule of the magic number still applies.
All right, and that is even more advanced than what the final project is, but it might help for you to understand it. So not final project, just the final thing we talk about, which is on, let's see, you're going to do a lab on this. It's calculating a /16 or /8 prefix. Let's keep talking. Not too much left here. Subnets to meet requirements. So as you work as a technician, you are going to be challenged with trying to determine how to break out a subnet properly, how to allocate the subnet to the configuration of equipment you have. So in this case, we have been given some addresses, not only for the gateway router to the edge router to talk to the internet, but also for a DMZ. Well, DMZ is equipment that you want the world, the public, to be able to get to because they're public addresses, like servers, without having to go through the NATing process and having it behind the router firewall in the private area. So it's called, they just call it a DMZ, and you can put public addresses on these devices. That's all they're talking about there. Here they're talking about minimizing unused host IPv4 addresses and maximizing subnets. And so again, when you're subnetting in the fourth quartile, in the fourth octet, you are going to start with a 24 that has one network of 256. 254 usable. You subnet that in half. That's a 25. That's two networks of 128 to 126 usable, et cetera, et cetera. And so when we have a network like these 5 addresses here in the middle, they only need 2 addresses. Now this example that they've given us here does not actually help us to understand about minimizing the waste of addresses, but it does show us a bit of a challenge. So because we need 10 networks, we have 10 branches, we have 5 branches and 5 connecting networks, we have 10 total networks. We can't use anything in the fourth quartile, so we have to octet into the third quartile. And so we're given a /22 to start with. And so in order to get 10 networks, what we do is we split that 22 network in half, and we've got 2 networks, split it again to 4, split it again to 8. Now we have 16 networks. And look, we have 64 addresses in each of the 16 networks. So that's a perfect subnet to be able to allocate our addresses. That's why each one of these is a 26, and you can see it goes up from 0 to 00 to 064 to 0192. I'm losing these here I'm sorry, to 0128 to 0192 to 1.0 to 1.64. So it is going up by 64 addresses. That's that block size I talked to you about earlier. So it is a little bit challenging, a little bit tricky, but if this is the hardest that you have to deal with, remember when you're trying to increase the just practice. That's all I can say about subnetting. Practice, practice, practice. And you're going to start with this packet tracer 11.7.5, where you're going to practice subnetting. and hopefully you do well with it. Now, I am not going to teach you VLSM in this video. There's a whole video just on VLSM, and I just want you to look at that. And I am not going to show you these because, again, it's in that video. I will just say in the VLSM, the key is creating or listing your subnets largest to smallest. And so in this example, you would start with 28 at the top, then 25, 20, 15, 2222. And by doing that, you allocate according to the largest block first, and then you're able to allocate. All we're doing with VLSM is we're saying, hey, we're not going to just use all the same size networks, right? If we use 4, 5, 6, 7 networks and use 30 hosts in each one, we would be wasting 28 hosts for each one of these guys, right? So there's no reason to do that. So what we do is we take one of the subnets, one of these blocks of a host, and we break it up individually. Now, in reality, it wouldn't be this 8th one here. It wouldn't be here. It would be, we use these 4, and then we're actually breaking up this guy. They just don't really show it quite right because that so allows for all of these addresses to be used later. If we were to say need another network of addresses, it would then fill into the unused addresses. That way you would not have to reallocate your addresses. All right, and that's all. I'm not going to, like I said, I'm not going to read that. They talk about structural design just briefly. They really talk about how you, as the network technician, has to be able to develop an entire IP address infrastructure for IPv4. You're going to do a VLSM packet tracer to show that you've actually learned this material. All right, so that is the end of our presentation. I'm going to stop sharing. On my end, that was a pain, and on my students' end, I apologize for dropping a couple times. You guys that are watching this as a recording, you didn't see the mess that we just went through. At least, hopefully, you didn't. There's not just this one video. There are 3 more videos that go in depth, even further on all the concepts that I talked to today. I highly encourage you to watch those videos. I personally, when I learned how to subnet, I kind of got subnetting, but I didn't understand how to VLSM subnet, so a virulent subnetting. And so what I ended up doing was watching about a half dozen people on YouTube trying to explain it in a simple enough way for me to be able to understand what they're even talking about with VLSM. And I got it. There's this one video that I included in my video, and that one video was an awesome way to learn how to subnet, talking about taking one big block and breaking it down and then allocating those blocks of addresses. So anyway, so I'm going to let you watch those other videos. It has been a pleasure to be your teacher today. My name is Don Lafond, Professor Don. If you have any questions and you are watching this presentation with me now, we'll have a moment for you to ask me those questions. If you're watching it as a recording, ask in the help discussion forums inside of NetAcad, or if you're watching it on YouTube, please ask in the comments. Also, please like and review my page and follow. I'd love to see you following, and you can get updates whenever I release a new video. All right, that's enough for tonight. Have a great evening, and thank you for coming to class. I appreciate it.